All right, and hi, and welcome to today's lecture. So it is July 1st. And today I'm going to be talking about row and column spaces. So 3 lectures back, we were talking about subspaces. So given a vector space, V, a subspace, W, is a subset of V that is closed under addition and scalar multiplication. So we've talked about several subspaces at this point. Today we're going to introduce 2 more. And the subspaces we're going to introduce are going to be associated with a matrix. So let's suppose we have a matrix A that looks something like this. Alpha 1, 1, alpha 1, 2, blah, 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 alpha 1, n, and then alpha 2, 1, blah, 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 alpha m1, blah, 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 alpha mn. So this would, of course, be a m by n matrix. And associated to A are 2 different subspaces. And one is the columns of A span a subspace of Rm. So basically what I can do is I can look at all the columns here. And I can take their span, and each of these columns individually is a vector with m components. So their span is going to determine a subspace of Rm. The other thing we can do is we can look at the rows. So the rows, and we can understand each row of the matrix as living in R to the 1 cross n, where you'll recall this is the set of 1 by n matrices. In other words, the set of rows with n entries. We can understand each of these rows as living in the space, and thus the rows of A span a subspace of Rm, or R1 times n. So we find these 2 associated subspaces. The first one here is naturally called the column space. And the second is called the row space. So one thing we kind of want to understand today is we want to understand what the relationship is between the column space in the matrix, the row space in the matrix, and what is the relationship between these two spaces themselves. And so we're going to try to answer all kind of three of these interconnections. So let's start with a simple example. I'm going to consider the following matrix. A is equal to 1, 2, 3, and then 2, how about 2, 5, 4. So my first question is, find a basis for the row space. And my second question is, find a basis for the column space. All right. So here's the observation we can make. Well, row operations preserve the row space. In order to understand why this is true, think about what row operations you have. You can multiply a row by a scalar. You can interchange two rows. And you can also add a multiple of one row to another. And if you think about what all these operations do, you can see that they can preserve the space spanned by the rows. So one thing we can do if we want to find a nice basis of the row space is we can perform Gauss-Jordan row reduction. So let's take our matrix A and let's find a nice basis of the row space. Well, we write down our matrix, 1, 2, 2, 5, 3, 4. First thing I'll do is I will set row 2 equal to row 2 minus 2 times row 1. If I do that, I get 1, 2, 3, 0, 1, and negative 2. So in this case, the next thing I can do is to put it in row reduced echelon form, is I can subtract 2 copies of row 2 from row 1. So I can set row 2 to be equal to row 1 to be equal to row 1 minus 2 copies of row 2. If I do this, I'm going to get 1, 0. Down here I'll have a 0, 1, a negative 2, and now I'm subtracting 2 times negative 2 from 3, and so I'll get 7 here. And this is in row reduced echelon form. So in particular, the first row and the second row are linearly independent. There's no way you can use the 0 here, or the 1 here, or the -2 here to cancel out the 1 here. Thus, here's what we conclude. If we set v1 to be the row vector 1, 0, 7, and we set v2 to be the row vector 0, 1, -2, these form a basis for the row space. Okay. So that completes the first part of our problem. Let's consider the second part. So I want to take all this, and now I want to find a basis for the column space. So in order to do this, what I'm going to do is I'm going to look at A transpose. In this case, A transpose is, we have 1, 2, 2, 5, 3, 4. And the rows of this correspond to the columns of this. So what I'm going to do is I'm going to perform row operations on A transpose. And the key reason I'm doing this, just to spell it out in detail, is that the column space, or I should say, the row space of A transpose is the same thing as the column space of A. And by this I mean there's a natural way to identify them, but I don't really want to get into that in more detail at the moment. But this is going to be an important fact for the rest of today. So let's compute the row space of A, or the row space of A transpose. So the first thing I'll do is I'm going to do the same kind of row reduction operation, and I'm going to set row 2 to be equal to row 2 minus 2 times row 1. And I'm going to set row 3 to be equal to row 3 minus 3 times row 1. And I'll get a new matrix. My first row will stay the same, so I'll have a 1, 2 here. And then I'll have a 0, 1 here. And then I'll have a 0, -2 here. Next thing I'll do is I will set row 3 to be equal to row 2 plus, I'll set row 3 to be equal to row 3 plus 2 times row 2. And I'll set row 1 to be equal to row 1 minus 2 times row 2. If I do that, I'm going to get 1, 0, 0, 1, and then 0, -2. Or, I'm sorry, 0. So, V1 equals 1, 0, and V2 equals 0, 1 form a basis for the row space of A transpose, which means if I look at the vector W1 equals 1, 0, and W2 equals 0, 1, these, being the transposes of these, form a basis for the column space of A. So note that the technique we used in both of cases of finding a basis for the row space and for finding a basis for the column space is the same. The only real difference is the matrix we applied it to. Here we applied row reduction to A to find our basis, whereas for the row space, and here we applied row reduction to A transpose to find a basis for the column space. This is how, in practice, given a matrix like A, you can go about finding a basis for these two associated subspaces. The next thing I want to do is I kind of want to get into the theory associated to row and column spaces. So let's get a bit of that. So I already stated this, but let me actually prove it, because this is our first important theorem. If we have two matrices, and these two matrices turn out to be row equivalent, then the claim is that they have the same row space. So let's suppose we have a list of vectors. So suppose V1 through Vn are row vectors of a matrix A. Then the span of V1 Vn is equal to the span of V1 blah 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 Vi plus M Vj blah 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 Vn. And so what we're doing here is we're doing the row operation that corresponds to adding the jth row to the ith row. And we want to show that this span is equal to this span. So here's why this is true. A linear combination of these vectors, or how about this? Let's look at a linear combination of these vectors. So say we have AI, or A1 times V1 plus A2 times V2, and then plus blah, 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 AI times Vi plus M Vj plus blah, 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 An times Vn. Well, this is the same thing as A1 times V1 plus A2 times V2 plus blah, 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 blah. And I'm going to rewrite this, and I'm going to keep the AI next to the VI. But then I'm going to distribute this term over to the vector involving Vj in the sum. So I'm going to have blah, blah, blah. And then plus AIM plus AJ times Vj plus blah, 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 AN times Vn. So what I've done is I've taken an arbitrary vector W, and my W lied in the span of these vectors. And I've shown that W in fact lies in the span of these vectors. And so this shows that this subset is contained in this subset. And it's not too hard to go the other way, because if I look at, say, W is equal to A1 V1 plus blah, 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 AN times Vn, then what I can do is I can rewrite this as follows. This will be the same thing as A1 V1 plus blah, 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 AI times VI plus MVJ plus blah, 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 blah. And here now I'll have AJ, and then minus AIM times VJ plus blah, 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 AN. So I've taken a generic expression for W that lies in the span of these vectors, and I've rewritten it as a vector that lies in the span of these n vectors. And so this right here lies in the span of V1 all the way through VI plus M, Vj, blah, 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 Vn. So I've now shown that this is contained in this, and this is contained in this, so they're equal. So this shows type 3 row operations preserve the row space. And we already used this fact implicitly in our previous calculation, or actually explicitly, since I did state it. Now, I'll leave it as an exercise to verify that type 1 and type 2 operations also preserve the row space, but both of those proofs are easier than this one. So this completes the proof of Theorem 3.61. And now we can kind of look at how it implies some further results. The first thing we're going to look at is the following definition, which is extremely important. And this is the notion. Let me minimize this. This is the notion of the rank of a matrix A. And it's the dimension of the row space of A. So what we're going to do is we're going to talk about how this works. The rank of a matrix is kind of a measure of the dimension of its image. So in order to make this more clear, let's think of our matrix. So let me go back up here and take our matrix. We have a matrix A. It's an M by N matrix. And we can think of A as a function. And it's a function that goes from Rm, or I'm sorry, it's a function that goes from Rn to Rm. And A determines a subspace of Rm, the column space. And what we claim that's going to happen, and this isn't proven yet, and so this is, I guess we'll say, to be proven. The rank of A may be understood as the dimension of the column space as well. So this is really the big result of this chapter. Not only does the rank tell us something about the dimension of the row space, it also tells us something about the dimension of the column space. And so the general statement we're going to kind of work towards proving is that these two spaces, the column space and the row space, even though they are different vector spaces, turn out to have the same dimension. That's our goal. Now, let's look at an application of the notion of rank. So here's the theorem we want to prove. So this is a relatively simple one. So theorem. A linear system AX equals B is consistent if and only if B is in the column space of A. So let's talk about how we can go about proving this. What we want to observe here is that if B, or sorry, I should use lowercase, if B is in the column space of A, then we have that B is equal to C1 times A1 plus C2 times A2 plus blah, 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 Cn times An, where the Ai are the columns of A. But we can interpret this as follows. We can take the coefficients C1, C2, blah, 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 and Cn, and we can arrange them into a vector. And so we get the vector C1, C2, all the way down to Cn. And this vector, this C vector, will satisfy the property that if we multiply it by our matrix A, well, it's going to be the same thing as the sum, which means it's going to be the same thing as B. So this shows that if B is in the column space, then AX equals B is solvable, aka consistent. Now, that handles one direction. For the other direction, let's say, suppose AX equals B is consistent, which again really means the same thing as solvable, in which case we have a vector x naught, x1, blah, 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 blah. All right, I'm going to start from x1, x2, all the way down to xn, such that times A, this is equal to B. Well, then we can understand the left side of this equation as x naught, x1 times A1 plus x2 times A2 plus blah, 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 xn times an, and this has to be equal to B, which means, of course, that B is in the span of A1 all the way through an. So this shows the other direction, that if this system is solvable, then B has to be in the span of the column, so it has to be in the column space. And so that proves this theorem. Here is the next theorem we want to look at on linear systems. So we're going to let A be an m by n matrix. And then the claim is that the linear system AX equals B is consistent for every B in Rm, if and only if the column vectors of A span R to the m, and the system AX equals B has at most one solution for every B, if and only if the column vectors of A are linearly independent. Okay? So let's see why this is true. So AX equals B is consistent for every B in Rm. Well, what this means is that by our previous theorem, it means that this is the same thing as every B in Rm lies in the column space of A. And this, so basically the first part of the statement follows immediately from the preceding theorem. Because if every B lies in the column space of A, this is the same thing as saying the columns of A span Rm. And so that completes the proof of the first part of this statement. Now let's look at the second part, which will require a little bit more work. Okay. So, what we're going to actually do is we're going to prove the converse. So, suppose AX equals B has multiple solutions. This implies, or I should say is equivalent to, by a result that we proved 2 lectures ago, the null space of A is positive dimensional. And of course, this is the same thing as there being non-trivial solutions of AX equals B, which in turn is the same thing as there exists AI, or how about this? I'm going to use a different letter. There exists CI, not all 0, with C1 times A1 plus blah, 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 Cn times An equal to 0, where the AI are the columns of A. And so this shows that this equation having multiple solutions is the same thing as a non-trivial linear dependence relation between the column vectors A1 through AN. And so that completes, and the fact that all of these are bidirectional implications completes the proof of the second statement here. So the interesting thing to note, of course, is the dimension of the column space, namely the thing, well, okay, hold on that. I'll come back to that after the next result. So, moving on. I want to look at a special consequence of this result. This will tell us that an n by n matrix, so a square matrix, is non-singular if and only if the column vectors of A form a basis for Rn. So let's see why this is true. Well, here's what we can observe. We may write A as a square matrix. C11, C12, C21, blah, 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 Cn1, and C1n, and Cnn. Now, if A is non-singular, then AX equals B. So I'm going to consider the matrix equation associated with this has a unique solution for every vector B which means the span of the columns is Rn, and not only that, it also means that by the previous result, because this has at most one solution, the columns are linearly independent. And since both of these conditions are true, they together imply the columns form a basis for Rn. Rn. So this result follows directly from the result we just proved. All right? And now we get to the big theorem, or at least one of the two big theorems. And this theorem is so big that it has a name. It's called the rank-nullity theorem, but I've heard other people call it the fundamental theorem of linear algebra. So here's the statement. If A is an m by n matrix, then the rank of A is the rank of A plus the nullity of A equals n. And so let me say what the nullity of A is. The nullity of A is the dimension of NA, which is the null space associated to A, which I'll just recall right now. This is the dimension of space of vectors X with AX is equal to 0. All right. So this is rank nullity. We want to prove this. Here is how we will prove it. Consider a matrix A. Or I should say, consider A, R, R, E. And this will be the matrix obtained from A after putting A in row-reduced echelon form. All right. So, associated to this is R and K, where R is the number of free variables in the equation A RRE times x is equal to 0. And then we also have the number of bound variables. And it's the same equation. Now recall that a free variable or a bound variable corresponds to a column of the row-reduced matrix that contains a 1 and nothing else. And that 1 is the first one of its row. So bound variables essentially correspond to leading ones, and free variables correspond to columns that do not contain leading ones. And every variable is either bound or free, simply by how we've defined it. So we have R plus K is equal to N. Now, R is going to be equal to the dimension of the row space, or I'm sorry, K is going to be equal to the dimension of the row space of A. Why is this the case? Well, A and the row-reduced matrix, or the row-reduced echelon form of A, have the same row space. So row space A is equal to row space ARRE. And in the row-reduced echelon matrix, every row is linearly independent. Every non-zero row is linearly independent. So for every non-zero row, you have a corresponding bound variable, a leading one. And so thus, K here is the dimension of the row space of A. And what we conclude from this is that R has to be the dimension of an A. So let's think about why this is true. Let x be a vector with arbitrary values in the position of the free variables. Then we may choose values in the positions to ensure ARRE times x is equal to the 0 vector. And not only may we choose these values, but these values are uniquely determined. So, in order to understand this in practice, it may be helpful to look at an example. Let's look at the following matrix in row-reduced echelon form. 1, 2, 3, and then 0, 0, 0, 1, 0, 5, and then 0, 0, 0, 0, 0, 1, 0, 0, 3. So this is a 3 by 6 matrix. And suppose I choose, so this right here, and this right here all correspond to free variables. So I can literally say, I'll have F2 here is free, F3 is free, the first variable is bound, the fourth variable is bound, the fifth variable is free, and the sixth variable is bound. And so watch what happens if I multiply this vector by this matrix. It tells us that B1 plus 2F2, oh, and I set it equal to 0. It tells us that B1 plus 2F2 plus 3F3 plus 3F5 is equal to 0. So this determines B1 uniquely in terms of the free variables. It also tells us that B4 plus 5B5, or plus FB5, is equal to 0. So B4 is uniquely determined by F5. And finally, it tells us that B6 is equal to 0, so B6 is uniquely determined. So all three of the bound variables are uniquely determined by the free variables. So we can basically choose the free variables to be anything, and then the bound variables will be uniquely determined. So the dimension of the null space is exactly the dimension of the number of free variables. And that completes the proof of the rank nullity theorem. All right. Now we're going to look at the next big theorem, And this is really the biggest theorem of the whole chapter. So if A is an m by n matrix, the dimension of the row space of A equals the dimension of the column space of A. This is really interesting because it tells us that, you know, it's going to be a proof of the claim I asserted earlier, which is that the column space and the row space, despite being very different vector spaces, living as subspaces of different spaces, ultimately will have the same dimension. So there is going to be a tight relationship between the row space and the column space. So here is the proof of this. Let A, L be the row reduced echelon form of A. In which case, we have that the row space of A is equal to the row space of AL. Now, further, we also know that well, we can also look at the matrix UL. So let UL be the columns of AL, or maybe I should state this slightly differently. Let UL be the matrix of columns of AL that are, or I should say that correspond to bound variables. So, here's what we learn. UL is obtained from AL by getting rid of all the columns corresponding to free variables. So we can also let U be the corresponding matrix obtained from A by deleting the same columns. Removed to obtain UL. So, the columns of UL are linearly independent because they all have a leading 1 in their own separate rows. So this tells us that the columns of U are linearly independent. But the dimension of UL is actually just equal to the dimension of the row space of A and actually, I'm sorry. The dimension of the row space of A is equal to the dimension of the row space of UL, which in turn is less than or equal to the dimension of the column space of UL. And let me just take this inequality to another slide. Which in turn is less than or equal to the dimension of the column space of A. So we can conclude from this that the dimension of the row space of A is less than or equal to the dimension of the column space of A. But now we can apply this to A transpose. And if we apply it to A transpose, we get that the dimension of the row space of A transpose is less than or equal to the dimension of the column space of A transpose. But this right here has to be the dimension of the column space of A, because the row space of A transpose corresponds to the column space of A, and likewise the dimension of the column space of A transpose corresponds to the dimension of the row space of A. So we in fact get that this thing right here is also greater than or equal to this, and because both of these have to be true, we in fact conclude equality. The dimension of the row space of A is equal to the dimension of the column space of A. And that completes the proof of this theorem. All right, now let's do some examples. So let's consider this problem. We want to find the dimension of the subspace of R4 spanned by these 4 vectors. One way to do this is to group these 4 vectors into a matrix. And so we have 1, 2, -1, 0, 2, 5, -3, 2, 2, 4, -2, 0, 3, 8, -5, 4. And so this space right here is the same as the column space of A. But we know that the dimension of the column space of A is equal to the dimension of the row space of A, which means we can in fact figure out the dimension of this subspace by figuring out the dimension of the row space of this matrix. And how do we figure out the dimension of the row space? Well, we simply do Gauss-Jordan row reduction. So we may solve this. If we do that, then we can go about this doing a sequence of matrix operations. First matrix operation I'm going to do is I'm going to set row 2 to be equal to row 2 minus 2 times row 1. And I'll set row 3 to be equal to row 3 plus row 1. If I do that, I'm going to get 1, 2, 2, 3. Here I'll have 0, 1, 0, 2. Here I'll have 0, -1, 0, and then -2. And then here I'll have 0, 2, 0, 4. And so the next thing I can do here is I can set row 1 to be equal to row 1 minus 2 times row 2. I can set row 3 to be equal to row 3 plus row 2. And I can set row 4 to be equal to row 4 plus -2 times row 2. If I do that, I'm going to get the following matrix. So here I'm going to have 1, 0, 2, -1. Here I'll have 0, 1, 0, 2. And then I'll have 0, 0, 0, 0, 0, 0, 0, 0. So we have 2 1s here, which means we have 2 bound variables. So this implies that the dimension of the row space of A is equal to 2. Which means we can go back over here and we can note that the dimension of the column space of A has to be equal to the dimension of the row space. And this subspace of R4 is precisely the column space, so we conclude that this subspace has dimension 2. And so this example illustrates how problems involving the columns of a space can often be studied, or columns of a matrix can often be studied in terms of the rows of the matrix. And we've already learned a sequence of operations that allow us to easily study the rows. namely Gauss-Jordan reduction. So that's the beauty of this theorem that we've just proved. And this theorem, together with the rank nullity theorem, really, in my mind, constitute the fundamental theorems of linear algebra. Okay, so let's do one more problem for today. I want to look at this matrix. And what I want to do is I want to find a basis for the column space of A. So there's two ways to do this. The way I'm going to do it is I'm going to note again that the column space of A is really the same thing as the row space of A transpose. Which means if I want to find a basis for the column space of A, I can do well to find a basis for the row space of A transpose. And then once I find a basis for that, I can translate it back for the column space. So the first thing I'm going to do is I'm going to compute A transpose. If I do that, I'm going to have 1, -1, 0, 1, -2, 1, 1, 2, 3, 0, 2, -2, 0, 1, 1, 3, 4, 1, 2, 5, 13, 5. So that's A transpose. So now I'm going to do a sequence of row operations to put this in row reduced echelon form. First thing I'll do is I'll set row 2 to be equal to row 2 plus 2 times row 1. I'll set row 3 to be equal to row 3 minus row 1, row 4 to be equal to row 4 minus row 1, and row 5 to be equal to row 5 minus 2 times row 1. And I'm going to do all these operations in batch and see what I get. First row doesn't change, so 1, -1, 0, 1. Second row, well, I'm going to get, for the first column, I'm going to get 0 all the way down. So, let's see. I'm going to get a 5 here. I'm going to get a 1 here. And I'm going to get a, wait, no. I'm going to get a 1 here. And a 4 here. Let me sanity check myself real quick. Yeah, that's right. For the next row, I'm going to get a -1, actually a +1 here, a +1 here, a 4 here. For the next one down after that, I'm going to get a 3 here, a 3 here, a 12 here. And for the next one after that, I'm going to get a 0 here, a 4 here, and then a 2, a 3 here, I believe. So after doing these batch row operations, I obtain this matrix. Now I can do some simple work, which is I can set row 1 to be equal to row 1 plus row 2. I can also set row 3 to be equal to row 3 minus row 2. And I can set row 4 to be equal to row 4 minus 3 times row 2. If I do that, I'm going to get 1, 0, 1, 5, 0, 1, 1, 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Oh, wait, no. 0, 4, 3. So let me just check one thing back here, make sure I did everything right. Okay. So next thing I'll do is I will simply set row 4 here, or row 5 to be equal to row 5 divided by 4, in which case I'm going to get the matrix 1, 0, 1, 5, 0, 1, 1, 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 3/4. And at this point, I could subtract the bottom row from this row and this row, and I would see that the matrix would be in row reduced echelon form, with this row, and this row corresponding to a basis for the row space. But to spare myself a little bit of arithmetic, I can actually just leave it as is, because I see that this row, and this row are all linearly independent, which means the vectors v1, v2, v3, where v1 is 1, 0, 1, 5, v2 is 0, 1, 1, 4, and v3 is 0, 0, 1, 3, 4, are all linearly independent. And in fact, they form a basis for the row space of this matrix. So I can take their corresponding transposes, and their transposes would be W1 equals 1, 0, 1, 5, W2 equals 0, 1, 1, 4, and W3 equals 0, 0, 1, 3, 4. These three vectors, W1, W2, W3, form a basis for the column space of A. And that completes the calculation. Anyways, that is all I have for you guys today. So I'm going to wrap up right now, and I will see you on Friday.